In this video I'm going to demonstrate how to use the EMMA equations to separate a hydrograph into three components: surface runoff, interflow, and groundwater. You can see here the spreadsheet that we'll work with. It's the same one that you'll see in the other video where I use the it's also the EMMA method, but the equations are handled using a matrix procedure as opposed to this one where we take the EMMA equations and we explicitly solve for each of the components. So in this spreadsheet we've got date, we got flow. The data is from Little Cannon River. Column B has the discharge that's measured at the gauging station. Column C is the concentration of chemical 1 that's measured at the gauging station on the same day as the discharge. And column D is the concentration of chemical 2 measured at the gauging station. Chemical 1 and chemical 2 have characteristics so that they are distinct from each other in terms of the concentrations in the source waters, so that you can actually separate out those from each other. Some of the other parts here, columns F through K, are just values that are calculated intermediate to calculating the flows in the equations. On the right hand side of the table or the spreadsheet, you'll see columns Q, R, and S. Those are the characteristic concentrations of the chemicals, chemical 1 and chemical 2, in the individual source waters: surface runoff, interflow, and groundwater. The concentrations are in milligrams per liter. You can see that they are distinct from each other, so that these sources do have distinct chemical characteristics. Column M through column O are already calculated discharges, so I've already filled that all in. I'm going to go through and explain how those were calculated. Okay, so what we need to do first is to look at the equations. This will be posted on the, besides being on this video, will be posted on the Moodle site for the course. Here's the set of mass balance equations that I showed in class. The first equation, Qt is equal to Q1 plus Q2 plus Q3, is the equation for the water mass balance. Qt would be the discharge as measured at the gauging station. Q1 is what we'll call the discharge coming from surface runoff. Q2 is the discharge from interflow, and Q3 is the contribution of discharge from groundwater. The second equation that's shown is the mass balance for chemical 1. So C1T on the left hand side of that second equation is the concentration of chemical 1 at the gauging station. That multiplied by the discharge at the gauging station is the mass load rate for chemical 1. And then the coefficients C11, C12, C13 are the concentrations of that particular chemical 1 in the surface runoff source, the interflow source, and the groundwater source, respectively. The third equation is the mass balance equation for chemical 2. Same kind of a description. Stuff on the left-hand side of the equation is measured at the gauging station. And then source water concentrations are for surface runoff C21, for interflow C22, and for groundwater C23. If you take these three equations, we got basically three equations. The three unknowns are Q1, Q2, and Q3. Everything else is measured in the equations. So we can take those three equations and we can solve them simultaneously. So you go through, and the details of this derivation will be posted on the Moodle site. Go through and you take the first of the three equations and you solve for Q1. Then you take Q1, substitute it into the second equation, and you solve that equation for Q2, and then you take the Q2 solution and substitute it into the third equation and solve for Q3. The result of that is shown here. Q3 is given by this ratio, or this quotient, and the A values are defined on the first page of this document. I'll show you in a moment what those are. The A1 and the A5 actually vary from day to day because they have in them the concentrations at the gauging station, whereas the A3, or the A2, A3, A4, and A6 values are all constants because they're just differences between the characteristic concentrations of the chemicals in each of the source waters, and you'll see what those happen to be. So we can substitute in here QT and then these other parameters, and that'll give us the discharge on a particular day for the groundwater, and then using that result for Q3 we can substitute it into the second equation. Q2 is equal to, we need the total discharge at the gauging station plus the Q3 which you just calculated, and that'll give us the discharge of the interflow. And then lastly, the discharge of the surface runoff is just going to be QT minus Q2 minus Q3. Both Q2 and Q3 were just calculated. So we now know what the surface runoff value is. Alright, so now we can go just up and look at the definitions of the A values. A1 is C2T, which is the concentration at the gauging station on a particular day, minus C21, which is a constant. That's the concentration of chemical 2 in the surface runoff. A2 would be C23 minus C21. C23 is the concentration of the chemical 2 in the groundwater. C21 is the concentration of the chemical 2 in the surface runoff. A3 would be equal to C22 minus C21, where C22 is the concentration of chemical 2 in the interflow. And of course C21 has already been defined. A4 is equal to C12 minus C11, where C12 is the concentration of chemical 1 in the interflow, and C11 is the concentration of chemical 1 in the surface runoff. A5, as I said before, A1 and A5 both vary from day to day because C1T varies from one day to day, and C2T up here varies from day to day. This is the concentration of chemical 1 measured at the gauging station, and then A6 is the difference between the concentration of the chemical 1 in the surface runoff and the concentration of the chemical 1 in the groundwater. So those can be defined, and if we go now to the spreadsheet, we'll see that I got A1, A2, A3, A4, A5, A6. The shaded columns are the ones that vary with time, because as I said before, A1 depends on the concentration of chemical 2 at the gauging station. A5 depends on the concentration of chemical 1 at the gauging station, and those vary from day to day. They are given by these concentrations here. So the first day in the data set is 455 for chemical 1 and 5.1 for chemical 2. 445 for the second day and 7.93 for the second day, and so forth. Whereas these others, A2, A3, A4, and A6, all remain constant because they're just a characteristic of these concentrations in the source waters. There's some differences that are calculated according to the definition. Alright, so I take those three equations, the one for Q3, Q2, and Q1. I solve for Q3 first. And there's an explicit expression for that, so that this expression in Excel would just be the implementation of that equation for Q3 that was given on that handwritten notes. Once Q3 is calculated, we then can substitute that in to calculate Q2. That again is the equation given on that handwritten notes, and then finally Q1 is just the difference between the total discharge, which is column B, and the values that were just calculated in column N and column O. So that gives us these discharges, and we can see, of course, they're varying quite a lot. The groundwater seems to be receding exponentially with time. Same with the interflow. Surface runoff goes down but then comes up very rapidly with some of these other events that are occurring. And that's it. Hopefully this is fairly straightforward as to the procedure that you use for doing this. This can be used for the case where we have three sources that we can identify distinct source characteristics, as has been done in this example. The case where you just have two sources is much simpler. The notes for that will also be posted on the website. If you have a situation where they have more than three sources, then of course we need more chemicals. So if we have three sources, we need two distinct chemicals. If we have four sources, we need three distinct chemicals. If we have five sources, we need four distinct chemicals, and so forth. Usually there isn't a situation where you try to separate out more than either just two sources or three sources. That's the usual situation.